let's go back a bit more in cosmic timeline now. So I'll discuss about the traces of early matter domination and through its impact on the decoupling of dark matter and formation of small-scale structures. So this talk is based on this recent work in collaboration with Deptosh from IIT Kanpur and his students Orpon and Sariful. So I will give first a brief overview of where basically tell you the main point of this work, and then I will go into the details of the discussion. So essentially, the existence of an early matter dominated epoch prior to the Big Bang nucleosynthesis impacts the thermal decoupling of dark matter. If the dark matter decouples during the matter-dominated epoch, then it undergoes an additional amount of cooling compared to the plasma temperature. And this additional cooling, the rate of the cooling, it depends on how entropy injection is going into the plasma during the reheating epoch. So this rate depends on the entropy injection, and this in turn actually reduces the free-streaming horizon of the dark matter. At the same time, there is another aspect of an early matter-dominated epoch, which is the matter perturbations grow linearly during the matter domination. Now, if you combine these two effects, the linear growth of matter perturbations and reduced amount of free-streaming horizon of the dark matter, this together tells you that there will be a boost in the sub-Earth mass halo population. And as a result, what may happen is amplification of the dark matter annihilation rates in the galactic centers, which are in principle should be able to give some probe to the early matter dominated epochs through, let's say, the Fermi-Lat observations. So that's the main point. It's extremely simple. Now I'm going to discuss the details, starting from the motivation for considering an early matter-dominated epoch. So this cosmic timeline have been shown several times in past 2 days, and most of the concentration was towards this region, which is more near to us. The constraints, observations on from cosmic CMB and let's say JWST and others. But these observations, they essentially constraints, or they essentially probes the much later time in the cosmology. But virtually there are no observations between the inflation and the Big Bang nucleosynthesis. So we almost know nothing about how the universe was in between these two periods. However, the most important thing is that interesting particle physics events, almost all of the interesting particle physics events, electroweak phase transition, QCD phase transition, maybe dark matter generation, baryogenesis, everything happened here. So it's extremely important to understand and probe this epoch of cosmology. So the lack of any observations leads to speculation, and one of the most popular speculation about how the universe was before the Big Bang nucleosynthesis is a matter-dominated universe, which is different from the usual lambda CDM cosmology, where after the inflation, an instantaneous reheating happened, and the universe was entirely radiation domination. It's a deviation from that. It's an alternate scenario with a matter domination. And this is quite natural in a sense, because if after the inflation, the inflaton has to sort of decay in a way to the thermal plasma and gives rise to reheating. But typically this process of injecting entropy into the plasma, it's not an instantaneous one. It takes time. And this epoch of reheating, it is essentially a matter-dominated epoch if the inflaton is a matter-like object. But there are many other motivated scenarios. various BSM scenarios predict metastable fields which can dominate the energy of the universe in the early universe. Examples are moduli, dilaton, curvaton. There are multiple. So there are plethora of scenarios where it can go on. And this leads to, after the inflation, this leads to a universe where where some oscillating scalar field is dominating the energy of the universe, and at some point it decays into the thermal plasma. It injects all its entropy, transfers all the entropy to the standard model bath, and its energy density sort of exponentially falls off, and the universe gets reheated into the plasma. The only thing that has to happen is universe has to be radiation dominated prior to the Big Bang nucleosynthesis to evade the constraints from BBN, and that's around a few MeV of temperature. So it has to happen before the few MeV temperature. Now, what's not so well established or well studied is how this entropy injection is happening. So most of the scenarios that people discuss is sort of a scalar field perturbatively decays through a zero temperature decay, and so the dissipation is just a constant. Dissipation rate is just constant. But it often happens that this is not true. In fact, in general, the rate of entropy injection depends on the plasma temperature as well as the expansion of the universe. So it depends on the field value of the scalar that dominates the universe. So there are different specific scenarios, specific models, and specific analysis using the thermal field theory, where you can actually compute how this entropy injection is happening. There are multiple papers. I have just put some of them. Some of the detailed papers are by Mukaida et al. But for our purpose, what I can do is we can just parameterize the entropy injection as a sort of a polynomial of with some t to the m and phi to the k, where m and k are some, let's say, some integer exponents. And if you take such a dissipation rate, then the temperature, the evolution of the temperature of the thermal bath, that actually depends on these exponents. It's a model dependent point. And I'll show how this, I'll show some examples of that. So the question is, what are the fingerprints of such early matter dominated epochs? Can we distinguish between these different scenarios? Can we actually pinpoint how the rate of this entropy injection was? So that question is the question that I want to answer, and for that we use the dark matter sort of as a probe. So let us look at how dark matter decouples during an early matter dominated epoch or in any non-standard scenarios. So thermal decoupling is essentially chemical and kinetic decoupling. And the chemical decoupling goes through number changing processes of the dark matter. So it's through the annihilation, for example, for thermal dark matter. And this process also sets the Rayleigh density. So chemical decoupling sets the Rayleigh density. And in a early matter dominated epoch, what happens is you are injecting entropy to the system. So the Rayleigh density becomes diluted. So what the Rayleigh that you expect in a normal lambda CDM cosmology, if there is some early matter dominated era, then the Rayleigh could be smaller than that. So as a result, for a thermal dark matter, for a freeze out scenario, you would expect you need smaller cross section, smaller annihilation cross section, and therefore smaller couplings of the dark matter with the particles in the thermal bath. If you consider a freezing kind of scenario, then the situation is opposite. Then you require larger cross section to produce the dark matter, and so larger couplings. In fact, this can be used to see if so freezing models then require really small couplings, right? But in the presence of such an early matter dominated epoch, you require larger coupling, and so some of the freezing scenarios which you have no hope of probing might come under the experimental radar if such an epoch is present. So this is all about chemical decoupling. Now let's go to the kinetic decoupling. Kinetic decoupling is decided by the elastic scattering of the dark matter with the particles in the thermal bath. And after the decoupling in a radiation-dominated universe, dark matter, the temperature of the dark matter redshifts as a to the minus 2, while the plasma redshifts as a to the minus 1. So the dark matter actually cools faster than the plasma. And this sets the free-streaming horizon of the dark matter, which also in turn sets the smallest scales at which you see some structures, because above this, below this free-streaming length, then all structures are washed out because of the velocity of the dark matter. So the chemical decoupling as the kinetic decoupling sets the free-streaming horizon. Now, in usual scenario, typically chemical decoupling precedes kinetic decoupling unless you go to some very light dark matter or something. So what happens in an early matter dominated epoch? So in early matter dominated epoch, so you have to actually solve the equation for the dark matter's temperature, the evolution of the temperature, and the solution actually, and this equation depends on the momentum transfer in the elastic scattering. So this momentum transfer can be like, you can have an elastic scattering with an S wave scattering or a P wave scattering or even higher wave scatterings, and the evolution of the temperature depends on it. So the solution actually involves two terms. The first one term is just goes as a to the minus 2, which is the usual. And then there is another term which goes as some a to the minus p, some other powers, and it depends on how the expansion history and the elastic scattering rate. So just for example, I've just given one example here. So let's say that this entropy injection rate, the dissipation rate just depends on temperature. In that case, the plasma temperature before reheating falls off as a to the minus half, and these are the these two lines are the evolution of the dark matter temperature for S wave and P wave scattering. And you see in one case it falls off as a to the minus 1, and in the other case it goes as a to the minus 2. And after the end of the reheating, then in both cases it goes to a to the minus 2. So in this case where it goes as a to the minus 1, we call it a partially decoupled dark matter. It's a partial decoupling. It's not as fast as a to the minus 2, and this is a full decoupling. So it depends. So how the dark matter decouples, it depends on how the universe expands and how the dark matter scatters, how the dark matter elastically scatters. So again, giving you two more examples. So where entropy injection rate is constant, in that case, S wave scattering cannot decouple the dark matter. P wave scattering can only partially decouple the dark matter during the early matter dominated epoch. While if the entropy injection rate depends on the temperature of the bath, then S wave scattering can partially decouple the dark matter, and P wave scattering can fully decouple the dark matter. All this leads to a reduction of the free-streaming horizon of the dark matter. So these are the three situations we are showing with different expansion history and with S wave and P wave scatterings. And this colored region in these three plots shows that where the free-streaming horizon of the dark matter is smaller than what you would expect in a fully radiation-dominated cosmology. But there is a catch here. The catch is that this sort of holds true only if there is a single process which operates both the chemical decoupling and the kinetic decoupling. If there are multiple processes present, some of which are dominantly contributing to the chemical decoupling and the others contributing to the kinetic decoupling, then it's not so easy to say that the free-streaming horizon would always decrease if there is an early matter dominated epoch. So that's the story about the decoupling and the free-streaming horizon. Now let's come to the what happens to the matter perturbations. So the matter perturbations actually grow linearly. The dark matter perturbations grow linearly during the matter-dominated epoch. So let's take this line. So around this point, the mode that we are interested in enters into the horizon, and then it grows linearly till the universe was matter-dominated, and then then it becomes radiation-dominated. And this linear growth in the matter perturbations, this can also be seen in terms of the power spectrum, where you can see that this red line gives you a growth, a deviation from the usual matter perturbation in the radiation-dominated universe. But there is an important point here. This growth is not, this growth cannot go on forever. It depends also on the free-streaming horizon of the dark matter. And beyond the free-streaming length, this actually sharply cuts off and just exponentially falls off. So this actually tells you that the matter power spectrum is enhanced during EMD in a range between the sort of reheating and determined by the reheating temperature and the free-streaming horizon of the dark matter. And this leads to enhancement of the halo population. So this object in the y-axis is called the differential bound fraction, which already I think Ranjan showed in the last yesterday. And you see the populations of the dark matter of the halos with mass below the Earth mass gets a boost within two scales. One is upper cutoff determined by the reheating temperature, and there is a lower cutoff, one should be lower cutoff, determined by the free-streaming length or free-streaming horizon of the dark matter. And the interesting point here is this green line. This green line shows that there is an upper value of a cutoff on the free-streaming length, beyond which you would see absolutely no structures. So we thought that this can be turned into a constraint on the parameter space of dark matter models, and that is exactly what we have done. We have taken two different dark matter models, very simple toy models. One is a scalar dark matter and one is a fermionic dark matter, and in the first case there is an SOF scattering and partial decoupling, and the second case POF scattering and full decoupling. And we show that actually we can find some region in the parameter space where the decoupling happens during the early matter dominated epoch, and there is some region, there is a line which separates this parameter space where you can actually see an enhancement in the small scale structures. So this is also shown in specifically in this differential bound fraction, and this is my last slide. So what we are now doing right now, what we are working on is to so we already found the boost in the structure formation, boost in the halo populations. Now we want to see how this affects the dark matter annihilation rates in the galactic centers. This actually depends on two competing effects. One is the lower annihilation cross section required to fix the relic density, and the other is the higher micro halo population. And one has to multiply both of them and see whether ultimately the boost persists or not. We are hopeful that this will be the case for certain kind of entropy injections, because, for example, if the entropy injection is proportional to temperature, then the annihilation cross section you require is actually greater than what it would be for a constant entropy injection. So this is an ongoing work, and this would probably give some more handle to probe this kind of non-standard cosmologies and distinguish different dark matter models. So thank you very much. Thank you for inviting me, and thanks for your attention.
Questions? So in all of these studies, you're already assuming that you have a standard model bath already formed. So dark matter is always weakly interacting.
Yes, here we are assuming that the dark matter is a WIMP dark matter. It's a thermal dark matter.
And then how is it ensured that always a bath will be formed? So it is the standard model particles are strongly interacting with your inflaton, or?
Yes. So the standard model particles are produced from some dissipation of the inflaton. That's the assumption. And also there is another assumption, since you pointed it out. The assumption is that the thermalization is instantaneous. So once the standard model particles are produced, they instantaneously thermalize. It's not always true, and those effects have also been studied by Deptosh and his students, and then there are also interesting things if you assume that the thermalization is non-instantaneous.
And what happens to this dark matter particles? So they are beyond standard model particles.
They're beyond.
In the inflaton phase, it was already strongly coupled with the inflaton. At some point, some decoupling happens. So how do you take into
So what we assume is that the dark matter is produced so dark matter is in thermal bath initially. It's a thermal dark matter, and then it's frozen out below, let's say, roughly the mass of the dark matter. When it becomes non-relativistic, it freezes out. That's the chemical decoupling. But chemical decoupling does not mean thermal decoupling. So then you need to also see when it decouples kinetically. And that's just the first remember.
Thank you.
Any other question? Yes, Ron.
Hi, thanks for the nice talk. So you said the kinetic decoupling using the elastic cross-section, but so I don't know about whether that effect is relevant here or not, but there is also another effect due to dark matter radiation coupling, which can produce acoustic waves, acoustic oscillations, and that will suppress the power spectrum. Is that relevant here, or do you know? I don't know the answer.
I also don't know the answer, but this happens much before the BBN. So
This also what I'm talking about is also with
so then I
BBN.
don't know the answer. Yeah.
But yeah, okay, thanks.
So one of the plots that you had, you showed the change in the power spectrum. I forgot if it came. Yeah, this one. So is the scenario that the changes happen without screwing up any constraints? Is that?
Yeah, because these are all happening before the BBN. So there is, I don't think there is any constraints on this kind of scenarios.
So meaning the change is at large scale, and so there are observations that don't yet constrain this.
No, because you see this, the boost in the halo masses, these are very, very small. These are sub-arc mass halos. So the large-scale surveys won't capture any of
Small
this.
K behavior would be standard.
Yeah. So the only way I think to capture this is to see the dark matter annihilation rate, and there may be some boost in there.